Okay, so we're going to finish with Michael. Michael's recently moved from NYU to Edinburgh. I'm pleased to have him in the UK. He's going to talk about multi-model mixtures and information theory.
Thanks. So thank you to all those who stayed until the last talk, and thank you to the other organizers for inviting me. As you can see, well, maybe you can guess from the title, I'm going to talk about something that's not even usual for me to talk about. It's going to be about multimodal ensemble modeling and bits of information theory. You might have noticed or not that the term filtering disappeared from the title. This is because I was more optimistic when submitting the abstract. And turned out I didn't have as much time to complete it. Anyway, so I might do some data simulation as I go along from you, but it's going to be mostly about predictions. So this is joint work with most of it, well, large parts of it are joint with Andy Maida from Quran. A bit of motivation before I go on to a few more details. So first of all, this is supposed to be a simple talk. So if I'm incomprehensible, it means I'm doing a bad job. It's not because the stuff is difficult. So you can stop me whenever something is unclear. So it sort of started in a context of I went to a couple of atmospheric meetings when I saw people running large simulations based on multimodal ensembles, and that got the thing going. And the main question was related to the following. I mean, so as common, at least in atmospheric sciences, so I don't think it's restricted to atmospheric sciences, not even to force dissipative dynamics, as far as I'm concerned. But the problem is the following. I mean, imagine you're trying to predict some very complex dynamics without knowing what your true dynamics is really doing. You have a bunch of models which to some degree have an error embedded in their dynamics. They don't correspond exactly to what you model, even on the reduced subspace of variables that you want to model. So you have a large number of different models, and you want to come up with the best prediction of the truth. Okay? And the question is now, you might for one reason or another have a model that you believe is the best one for doing predictions, but there is a bunch of other ones. The question is, can you do better by combining all these models or just using your favorite model? Okay, so the statement is pretty simple. So I'm just trying to sketch it. I'm not a great artist, so let's imagine that this red shadow here corresponds to the true probability density, and all these other guys are imperfect models. So now I'm just sort of sketching the intersection, so that my truth is this red guy here, and I've got a bunch of probability densities at the end. Well, and I would like to get some kind of criterion that would let me decide whether I'm better off using my single model that I consider the best for whatever reason, or maybe I should combine number of my imperfect models in the hope of predicting the dynamics better. And I'll clarify in a second what I mean by predicting it better. There will be bits of stuff borrowed from information theory, which I will use in this context. Well, so I want to get some kind of, it will appear at some, well, a couple of slides down the line, a condition which will effectively let me decide. So this was going to be mixture density corresponding to my multimodal ensemble. Here I'm going to have my single model. I would like to be able to tell under what circumstances I'm doing better using my mixture models versus a single model. So this is a common situation in various, at least again, atmospheric situations. There's some paths of hurricane. This is maybe more familiar to at least people in atmospheric sciences. The mean, well, that's the mean global temperature. So this period here corresponds to the time interval over which you can actually observe and acquire some empirical data. And from then on, you start predicting. You're in a purely predicting mode. And as you can see, well, there's a bunch of different models that were all tuned within this time interval according to certain metrics, which I don't quite agree with, but anyway. And then once you keep the dynamics running, well, it's not a surprise that these things separate. But the question is now, So assuming you have this bunch of models, and the most common thing, because it's not quite obvious how you should weigh the models. So you have a number of them, you know they all make an error. How should you weigh them? But it's not that clear at all what weight should be associated with. Yes?
So your bunch of models, should I be thinking of a model with varying parameters or just...
No. Okay, thank you. For this talk, actually, again, this is another simple thing in this talk. There's effectively going to be no dynamics involved. I'm not going to use that. I'm just going to assume I have a bunch of models. I'm not even going to go into details too much of what these models are doing. I'm really concerned with, I'm stuck with a bunch of models. Now there's a question, first of all, can I weigh them in an optimal way? I'm not going to play with the parameters of the models themselves. Okay, so I'm not, in this part, in this work, there's nothing done to the models themselves. I'm not going to...
They don't differ in their parameter settings.
They might. Well, it depends what you consider to be your family of models. They can be completely different models. They can be sort of one parameter family of models, sort of sampled, usually not continuously, but at this stage it's not important.
So for example, we could have two different implementations.
Yes, you could have two different implementations. Yes, for example. Or you could have two different GCMs. And that's actually how it started. I mean, there were various groups, each one of them had a different GCM, and they claimed that they are better than the other ones. And because they couldn't agree, they would weigh them equally, so that there is no global general circulation model. It's in atmospherics. Because they couldn't agree who was better off, they would just take equal weights, and everyone was happy.
These are time-dependent order distributions or equilibrium.
So, okay, now in principle, I'm just not these spies. In a second, I'll get to the probability densities are going to be time dependent. The main thing is that I'm going to have two phases. I'll get to this in a second. There's going to be a phase within which I assume I have some empirical data, which I can use to tune my models. So at least I can check how bad or good they are, and then I'll try to deduce something about it later on. My last motivational slide, just to show you an example how badly you can go with multimodal ensembles. I'm just showing a simple dynamics. I'll get to this in a second. So this is just an error. This is the error in time. So you can consider that I'm sort of running dynamics from this point on. Okay, so this is what the zero corresponds to here. The green curve is what I consider to be, for whatever reason, my best single model. Okay, the blue curve is my equally weighted multimodal ensemble. And these are just two different examples. I'm not going to go into details what I did here. The different instances, different type of dynamics. But you can see that in this case, I just took, and here I'm plotting the weights, by the way. Okay, so these are the weights of the models in the ensemble. So the blue one has equal weights. The magenta one is an optimal one, which I can, in general, in principle, I do not know what it is. I mean, in this case, I'm okay because I know what my truth was. But it's just to illustrate the thing. Okay, so like for this particular type of dynamics, the blue curve, and this is the error. So I'm actually, by just taking a bunch of models, weighing them equally, I'm actually making a much smaller error than for this single model that I consider to be the best. But what I mean by model to be the best, for example, the simplest example is you look at the correlation time of your process. Okay, so it's going to be some maybe simple stochastic model that has the correlation time that is deduced from the dynamics you're looking at, or something. It's not that important, but it's something that
So your error is not called that libel divergence?
It is. I'll get to this in a second. This is just an example to show that there might be two different situations, at least. I mean, so in this case, I'm lucky, but it very much depends on the choice of the ensemble. If you do it blindly, you can be okay, or you can do a pretty lousy job at this. So in this case, again, this is the error that I'm drawing here. So anywhere sort of starting from this time onwards, my multimodal ensemble, the equally weighted multimodal ensemble, is doing much worse than the single model that I chose to predict my dynamics. So this is just supposed to illustrate is that it can go both ways. And if you just think that whatever the problem is, just throw a multimodal ensemble at it and it's going to do a better job, that's obviously not true. But yes?
Do I understand this as overfitting?
No. It's not even. It's not overfitting. I mean, it's just you pick bad models, right? I mean, it's a pretty simple statement. I mean, if you choose bad models, you're not guaranteed to do a better job, right? I'll get to this in a second.
I don't understand, which is how come the optimal weight can have a bigger error than the single model? Isn't the single model in the class of the optimal weight? I mean,
Not in this case. No, it doesn't have to be. Oh, okay. Sorry. I mean, well, first of all, it doesn't have to be. The other thing is that what I'm choosing here, this is the optimal weights over the whole time interval.
Okay, sure.
Right. So that in this case, that's the reason.
It's because that green curve has that big spike in the beginning, in the upper right?
Well, yeah. I mean, okay. Let me speed up a bit. So I just wanted to say a few words about this the way I thought this might be tackled, and then I'll get to a simple condition that is sufficient for the utility of multimodal. Whenever you see MME, it's multimodal ensemble approach. A simple condition guaranteeing that, given a particular multimodal ensemble, you're actually going to do better than any model that you chose, the single model that you chose to run your predictions with. And then I want to just give a very simple example, sort of toy model example, that hopefully will clarify in more details what I'm talking about. Well, this data assimilation got shaded. I think there is, that's what I'm working on at the moment, but it's too early to say. So yeah, the whole thing is going to rely, it's going to be simple in the sense that, first I'm going to work within a framework, within information theoretic framework. And a lot of the conclusions will rely simply on convexity. That's just maybe worth remembering. Before I go on, if anyone of you has not seen the KL divergence or relative entropy, I'm just writing it down here. Okay, it's functional on the probability, on probabilities. Let's say they're all in some suitable Hilbert space. Okay, so this is my true probability, this is my model probability. And it can be interpreted as the lack of information in my model probability relative to the truth. Okay, I'm just sort of sketching it roughly here. And in particular, the truth probability you can think of as a marginal probability on the space of resolved variables. Okay, whereas the model is running purely on the resolved variables. If it's a reduced model, it's very likely it will diverge very quickly if I'm not filtering, but that's not important for now. I'll tell you in a second why I focus on relative entropy. It has a number of nice properties which help me quite a bit. Okay, before that, both of these correspond to large lack of information. Okay, so what I'm just trying to stress here, that this large lack of information can correspond to either it's a combination of wrong mean, wrong variance, or combination of any problems in the moments. It's not focusing on each statistical model independently. So like in this case, let's say I got the mean right, but I got the variance very wrongly. Here it's sort of more the variance is okay, but the mean is completely wrong. Both of these cases would be picked up in relative entropy as models with large error. Okay. So it has nice properties. Two of these nice properties. It's not a metric. It's asymmetric to start with, but it's non-negative and zero. Only the two densities are identical. And it's also invariant either under nonlinear changes of variables, which is important not for this talk but for other purposes. So okay, quickly, how do I define? Okay, let me start from a class of models, which I have a particular class of models in my ensemble, and pi corresponds to the true probability density at this stage. So it's quite easy to define abstractly what I consider to be my best imperfect model. It's the one that minimizes relative entropy over the class of imperfect models. Well, that's easier said than done. I mean, of course, what I'm doing here, I do not really know what this pi is. That's my true density, which I assume I do not have access to. What comes to my rescue is this formula here. I'm not going to prove it, I'm just writing it down here. The important thing is that I can rewrite my relative entropy as a sum of these two terms. One of them involves the truth and what is called the least bias density based on number of constraints. And the second part involves only this least bias density and the model itself. Okay, so once I cannot do anything with this one unless I do more measurements of the truth, I can play with the second term and try to minimize it, because I assume that I have access to this guy. This is the guy I can estimate in my training phase when I have empirical information and I have my models. So, oops, So I can try to estimate this. So, okay, that's the plot I tried to get to. So what I'm going to talk about for the next few slides, I divide the problem into two phases. Okay, so the one between the dashed lines, I'm going to call it the training phase. So this is the time interval within which I assume to have access to some empirical data. Okay, and then of course, and after the dashed line, this would be the sort of prediction mode when I don't know much about it, I'm just running it. And of course, what I would like to get is some kind of guarantee that if I do the right things with my model or models within this interval, I can say something about what happens later. That's part of the problem.
What's the abscissa in the upper right that you're pointing to? I just can't read the axis. Oh, it's time.
Yeah, it's time. So this is in time, sorry.
And so this is a probability of...
Well, I'm just sketching, so consider it, yeah, it's supposed to be some kind of trajectory in the space of probabilities or whatever. I mean,
even though that's
it's a
function,
sketch.
this is just
I can't sketch a probability density really.
clearly not.
So, so I'd like to first concentrate on this, and so that's what this part comes in. Okay, I can try minimizing this part of my model error within this time interval when I have access to the empirical data.
Pi m here is any probability measure, or is it also?
Pi m is my model. Sorry, pi m is model. Pi l is the least bias density.
So the model doesn't have to be a least bias.
No, in general, no. It's nicer if it is, but it doesn't have to be. No, in order for this to hold, you just need to have the least bias density of the truth. To rewrite it this way. This pi m can be anything.
What does least bias mean then?
That's what I'm getting. So least bias, I should probably write. So the least bias density is a probability density that maximizes Shannon's entropy subject to given L constraints. So in particular, this could be the first two constraints. If you, for example, try to find a maximum probability density maximizing Shannon's entropy is subject to constraints on the first and second moment, you're actually going to get a Gaussian.
Then minimize the L distance between pi L.
No, for now it has nothing to do. This pi L is really, if I consider pi L's, I'm going to be able to rewrite it in this form. Okay, and then the minimizing part will come later. This is not important at this stage.
But it's also true that the Gaussian minimizes p pi L, overall Gaussian. If you match the moments. That's true. But in principle, I don't have access to this part anyway. I just want to I'm using this, and that's why I'm using relative entropy, because I can peel off, I can sort of separate these two things. I'm assuming I don't know much about all of the truth. All I have access to is some reduced measurements of the truth. In particular, the best job I can do is to measure a couple of first moments. Okay, and once I construct those least bias densities, I can split my expression for the model error into these two guys. This one, that's why we call it information barrier. I mean, you can't touch it really unless you make more measurements. But then based on this one here, so once I know what my pi L is within this interval, I can try minimizing the model error within this interval given pi L. Okay, and I assume that I can do something with my model's pi m. Let me maybe skip this because I'll get to this part. Will be a bit faster. So why? And I'm not going to go through the details of this. I just want to point to a particular property of this procedure. So it can be shown relatively easily. I'm not even calling it a theorem because it's too simple. But it can be shown that if you optimize your model relative to this least bias density within the time interval, this calligraphic I here, okay? So then the model error, and there's two different cases. Imagine the two different situations. Now we had the training phase, and then we perturb the attractor, and we want to see what happens, how well do these optimized models approximate the perturbed invariant density. Okay. The other thing is you can imagine that this was not at all at equilibrium. It's just this was my time interval within which I had observations, and then I'm running it from a given initial condition later on. The difference here is that
if I assume, let's consider the sort of the linear response type thing when I'm perturbing my attractor. If I have enough, if my dynamics is sufficiently nice, in particular as shown by Martin Heider actually and Andy, if you have a sufficiently nice system that constrains it to pretty much in autonomous systems with hyperelliptic noise and a spectral gap condition out on the evolution semigroup. But then you can show that at least that as you perturb the attractor, the perturbation is going to be smooth, and effectively it gives me a bound on those changes in the this is a vector of all moments that I'm considering. Okay? So it effectively gives me a bound on this delta E, which is induced by the external perturbation. So in effect, if I do this sort of in the force response scenario, I can find I have a guaranteed bound on delta E throughout. Otherwise, I would only be able to predict within a sufficiently short time interval within which these guys are small. The main thing here that I want to point out is that I can rewrite this error in the following way. So I'm writing the whole thing in terms of these least bias densities. This represents the evolution of the perturbed moments in L2 norm over the interval I. But these guys are the Lagrange multipliers, which were actually optimized within the training period. Okay? So it sort of extends this result. So by tuning my model within the training phase, you can show that the model error passed the training first in the force response scenario will remain bounded as long as the changes in the moments are small.
The
Yeah.
error is also defined in terms of relative entropy here.
This is relative entropy integrated over time.
Right over time. Okay.
So that's sorry, I should have mentioned this. What about multimodal? Similar thing can be done in the multimodal framework. Again, so this pi here is relative entropy integrated over the whole time interval. I again tried sketching all those guys here. What I now am going to do, I again split this model error in these two parts. So the first one is just the integral of this relative entropy involving a truth and its least biased estimate. And the second part is the one involving the least biased estimate, and in this case the multimodal ensemble, which has the form of this mixture density. I'm not assuming Gaussianity at this stage. But all I'm going to do now, I'm assuming that my models are fixed. I'm not tuning any internal parameters in the models. All I can do is I'm just going to tune the weights, or that's all I can do. Okay. So effectively, I can try minimizing the error just by minimizing over the set of weights here. Is this relatively clear, or does anyone have a... So again, a similar story which goes without the proof here, because I can show this in detail, but it's simple. It's effectively so you can show a similar thing here, where now again these Lagrange multipliers are the ones determined in the training phase, and here again this is the vector of moments after the perturbation. Okay, but I have a bound, so I have I have a link between optimizing models within the training phase and how well my predictions would do after I perturb the attractor. Okay, so that's something nice that one would want to have in order to to run these procedures. Now let me get to this condition that I mentioned at the very beginning. So this is a slightly different take on it, which, I mean, it is linked, but maybe I'll do it step by step. So now this is what it means for me that multimodal predictions are better, or that let's fix to the training phase for now. So this is what it means to me that the multimodal ensemble does a better job at predicting the truth than some single model, this M diamond here. So I want to have the model error between the least bias density and the multimodal ensemble to be smaller than the model error in the single model predictions. That's as simple as it gets. Okay? And I would call it that's a necessary condition for improving my model fidelity over M delta, M diamond. I'll get into a sufficient condition. This one is not particularly tractable. I just wanted to sketch a few things. Again, I'm not good at plotting functionals over infinite dimensional spaces, so I decided to just do a two-dimensional representation of this. But one thing that will help me quite a bit, actually most of it will hinge on this result, is that relative entropy and its integrals as well. You can show it that it's a convex function. In particular, it's a convex function of its second argument. Okay, so that's what I'm sort of drawing. So I'm drawing these convex shapes here. So if, for example, this M diamond is this green dot here, okay, and this is my truth here. So you can, for example, see that, like, if I were to, and this, so the vertical axis here would correspond to my model error at a fixed time in this particular case. So now the question is, well, and the dots are the models, the possible models I could take into, including my ensemble. It's not a continuous family, it's just a discrete number of models. So in particular, you can see that if I were to combine, even if I were to retain this guy in my ensemble and combine it with this one here, if I chose approximate weights, I could reduce my model error by quite a bit. Okay, I could even beat my single best model, which is sort of sitting here. Again, if you look at it in the sort of, call it a vertical view, again, it's just a two-dimensional representation of it. So this is my green dot sitting here, and these are my sort of models sitting on an isocontour of relative entropy in this case. Of course, this is just to clarify one point. Let's say I picked my weight so that, you know, I'm sitting directly, you know, in this projection I would be sitting here. It doesn't necessarily mean that I recovered my perfect model, right? I mean, it effectively means that I can be anywhere along this line in this cartoonish example. But, is there a question? No. In particular cases, well, the thing I wanted to draw your attention to is that there's two cases. I mean, in a nice situation, as long as I can sort of grab something from the opposite side, if you like, of my truth model, I have great chances of reducing my model error. Okay. Of course, if I were to mix this model with this one, I'm not going to do any better. There's another trick here, of course, that, well, in this case, if I knew where I am in this whole space, even if I choose something with a larger individual model error, I could combine them in such a way to reduce the model error. But that proves to be quite tricky. I don't know how to do this in order to find a condition satisfying this. What I can do, though, is I can reduce it to get a sufficient condition for this, which effectively restricts. I'm not taking any models which are, if I were to, this is my starting model. I'm not going to take any models which have larger model error than my reference model error. Okay, and the sufficient condition can be determined simply from the convexity of relative entropy, and it's written down here. Yeah.
Can I be a bit concrete? If you had
Yeah,
two
go ahead.
moments,
Yes.
then the pi L would be Gaussian, and imagine your pi m's were themselves Gaussian, as might come out of the NKF. Then you could explicitly minimize over several ENKFs.
Look, that's why filtering was in the original title, and that's why I moved it. I am thinking about it, but I'm not there yet, because there's a number of different issues one can look at. I mean, just to cut in, you can, if I use relative entropy, I can only look at the. If you're talking about filtering, I can only look at the statistics of my filtered signal, at the marginal statistics of my filtered signal. I can look at other things. I can look at the pointwise things as well. If you see what I'm. Because as long as if I'm in the relative entropy mode, I'm looking at probability density of the signal. I'm not going to look at pointwise accuracy between the truth and the density. I'm really looking at the one-point statistics of my truth at a given time and one-point statistics of my estimated signal at a given time. But I'm not looking at their correlations. And you can do more by looking at other things. But if you stay in the relative entropy world, it's one thing to improve using multi-model, but just running number of, even in the common world, if you're running mixture models, mixture filters, you can improve the statistics of, I believe you can improve the statistics by running appropriate mixture model of your of your simple filters. But
Even if you weren't doing filtering, if you just had the mean and covariance
yeah, of course.
on the attractor, then you could.
Yes, yeah. This is roughly what this is about.
Then it's computable, right?
Yes, yeah. Well, I'll get to a Gaussian case if I'm kind of running slow, but I'll get to a Gaussian case in a second, so I'll show you what the thing I wanted to mention, so yeah, the main message is one can obtain a sufficient condition. It's not a necessary condition, as I say, because I could be, in this simple sketch, I could be somewhere here and still get a reduction of error. By reducing it into this condition, I'm really truncating I'm throwing everything that has a larger modular error. This at least makes sure that I'm sort of staying in this contour here, if I look at this. Okay? But then again, I can do, even within this contour, if I just combine these two guys, I'm obviously going to do much worse than if I combine this guy and the other guy. But this condition at least ensures me, when I'm doing better relative to any single model that I choose. Okay, you can kind of make it look fancy and write this statement in the most general terms. This is all written in terms of least bias densities. And here, sort of going back to your question, so in this particular case, I wanted to write everything in terms of least bias densities. I do not assume that my pi m's are least biased. That's why this first term comes in here. It effectively quantifies the difference between between the model and its least biased approximation. If my models are already in the least biased approximation, then I'm getting rid of this first term altogether. If, for example, if I were running Gaussian mixtures, then I don't have a problem with this one. But so this is in a general case. It's not practical in a general case because often I simply do not know how these moments evolve. I do know how these moments evolve in particular when I look at linear response theory when I perturb the attractor. And if I know that the perturbation of the attractor is nicely behaved in a sense that it's smooth, that it's smoothly perturbed. The invariant measure is smoothly perturbed. Okay, I've got like 5 minutes. Yeah, I started later, I think.
You have about 6 minutes.
Okay. Something that I want to use the simple model and show how this sort of issue of information barriers can come into the problem. So it's going to be related to, before I even start, there's going to be two different situations, which I'm again sketching here. So this is, again, you can think of it as this sort of this relative entropy, and I keep this convex shape here. Now, if the situation is such that I am able to sort of pick my models sort of on both sides, the truth is always on the bottom, or the estimate of the truth is on the bottom. If I'm lucky enough to pick my models on both sides of the minimum, then I can do great things. But it so happens that in a number of cases, I'm simply constrained. If I choose a wrong family of models, I can be confined to be just on one branch of those guys. And then no matter what I do, I will not do better. I mean, I can still do, if this is my reference model, I can do better than using this guy, but I cannot beat my single best model, which is the red one here. So if I have this sort of so-called information barrier in my problem, I'm actually going to be the best strategy is to use your best single model.
But you're assuming that your alphas are positive. Can you, if you make them negative, then you can...
I'll show you, yeah, well, no. If I make them negative, then I will not be, then the situation becomes, my convexity arguments will fail at that point. Okay. So my condition for assessing the performance, or at least trying to bind the performance of the mixture density based on the model errors of each model in the mixture. If I start looking at negative weights, I'm losing the whole band. So that I can't do. I'm not. This is just a sufficient way of sufficient condition. It's by no means. Anyway, so simple Gaussian system with a Gaussian attractor. So I have two variables here: additive Gaussian noise in what I call the unresolved dynamics. And I'm looking at U here. So you can think about U as the resolved dynamics. And my family of models is given here on the bottom. So I'm only modeling the U dynamics. Okay? And the models I'm using have three parameters. This gamma, some forcing, and the amplitude of the stochastic noise. So it's a sort of three-parameter family of models. And I want to model, in particular, I would want to model the response, the force response of the truth in the variable U here. I will not go through maybe too many details, but one thing is that, okay, I can compute the equilibrium statistics, the second order equilibrium statistic of my truth in the U variable of my truth. Okay, and then I can force my reduced order model, this one-dimensional model, to have the same marginal statistics in this variable U on the attractor. And this is done here. Without, the details are not that important. So it's kind of sort of doing pretty much the same, this kind of thing. So let's say my truth has this, probability density on the attractor, my model is here. By tuning the parameters in the attractor, I can make the marginal statistics agree. Of course, if I now were to change the forcing in the truth, I have no guarantee that my invariant measures after, at infinite time, after I stop changing my forcing, that they will agree. But what happens here is the following. So I have two constraints and I had three free parameters in my simple model. So even by tuning the means to the correct ones, means of U, I'm still left with one parameter, with this gamma guy here. So I still have a one parameter of imperfect models which correctly reproduce my equilibrium statistics, right? And well, I have one free parameter, so one might think that, okay, so if I now perturbed the attractor, I could perhaps at least get the infinite response right. I still have one parameter. So I can compute those. It's a simple model. I can compute what the changes in the mean are. And I can compute what the infinite time error in the predictions using those tuned imperfect models would be. And it's just given here. And the problem, well, the trick is that how well I do depends on effectively certain aspects of the unresolved dynamics, in particular this scalar A here. Because you can see that there's two different cases. If A is greater than 1, then no matter what I do with my gamma, I mean, the only way that I can minimize it effectively. There's no finite value minimum of this function. I would have to go with gamma to infinity, and that's the only minimum I can attain. If A happens to be negative, then I can find a unique value of this parameter gamma in my reduced model that will give me a zero error at infinity for the forced system. Is it reasonably clear or not? Because this example is supposed to be. So this is the model error at infinity after I stopped changing my forcing and I waited until it settled onto the new attractor. And I'm computing what is the model error between my tuned models and the truth. Okay, and I could compute those directly, what the change in the mean would be, and you can use those in the relative entropy expression. But it turns out now that depending on what this hidden parameter A was, I can either find I can find the right parameter gamma here that would give me the right force response at infinity or not. So in one case I will have. So it's kind of okay. I'll jump quickly. So there's going to be two different situations here. One in the case when I don't have information barriers. Sorry. So first I'm going to show this guy here. Okay. So in this case, in particular, I can find actually I have this. I can find an imperfect model with the value with a last free parameter gamma that will give me perfect response at infinity, and I have no information barriers in the system. And I can now look at various scenarios when I ran different ensembles and try to predict the force response. And I'm sketching what kind of ensembles I picked again on top here. And then this is my single model that I chose, and it is the one that has the right correlation time on the unperturbed attractor. This is the one that people would often choose to add, in reduced models. Now, if I were to add anything that has shorter the correlation time, which effectively lies on this side of this model here, I'm actually going to do much worse in terms of model error when compared to the single model predictions. The single model predictions are this green hidden by the magenta guy. So in particular, again, these are the weights of my ensemble here, the equal weight ensemble. The magenta one is the one with the optimal weights. I can do the optimal weights because I know what the truth was, but you can see what happens is my optimal weights effectively coincide with a single model that had the lowest error. Right? So in this case, it doesn't make any sense to use multimodal ensembles because I'm going to do worse than I would using any single model. If I choose my models more wisely, I can actually do quite a bit better. The error of the single model goes through the roof there. Well, small numbers, but it's much bigger than the equal weight model. In both these cases, I'm not going to go into details, but in both these cases, I'm spreading my ensemble more wisely. The message is here that you have to actually, multimodal ensembles are not always a silver bullet. I mean, you have to be careful. It's not always the case that if you just take sufficiently many, which is kind of obvious, if you take sufficiently many models, they're not guaranteed to give you a better answer than using a single model that you chose correctly. On the other hand, if you choose correctly your multimodal ensemble, and you can check this by just comparing looking at the model that are using this information criterion that I showed you at the beginning, you can make sure that you will be doing better. The final slide, and I'll be finished after this. This is the case when I do have an information barrier. So in this case, no matter what I do, I cannot find any model that will lie on this side of the branch. In this pictorial, this is just a sketch, of course. So what you can see here, that no matter, so I can only, so this is again my reference model, which is the one with the correct decorrelation time. And now I'm choosing, just to show, I'm choosing models which have, both of them have lower error in the KL sense. And in this case, all of them have a higher error in the KL sense than the single model I started with. Well, okay, so if they both have a lower error, of course I'm going to do better than the green guy, but I will not do better than the single model that has the lowest information, that has the lowest model error. In this case, again, I'm doing worse no matter if I choose the models on this side. I can't improve the predictions at all. So this was the case with this so-called information barrier, which in this case I could figure out that I have this information barrier because it was a simple model. So I could see that I cannot simply go onto this branch because no matter what the value of this damping parameter was, I could not have models that would be on this side of the branch. That's probably not that important. Let me just finish with a few conclusions. So I can go back to this sufficient condition if anyone is interested. It might have been too quick. And I want to stress that this is a sufficient condition. It's not a necessary condition, but this is at the moment as good as I can get. I don't think it's that easy to do anything tighter. The multimodal framework can be useful, but one has to be careful, and in particular using this information theoretic measure of the model performance can give you some insight and at least tell you where not to use a multimodal ensemble. And finally, I think that there is, well, at least, yeah, I believe there's some interesting things that can be done in the filtering framework using this, at least in terms of optimizing the statistics of the filtered signal and other things. Thank you.
Thank you. Any questions?
So, one of the reasons to use the multi-models, more than one model, is the realization that if you just do one model wrong to do a prediction, that it's nonsense, right? It doesn't. There's no. It's not science. You want to know error estimates, etc. So that's one of the reasons.
Yeah.
But what you're optimizing is alphas. So you get the best mean, let's say.
In this particular case, no, I don't get the best mean, and not necessarily, right? Because I'm optimizing weights in the mixture density. So I'm not just optimizing. Well, I'm optimizing more than that. But
yeah.
Sorry, this got.
Okay, so I'm just thinking about. Okay, so well, perhaps I misunderstood. I didn't think this through, but. You're looking at
Each model is itself a probability distribution.
Exactly. So each model is a probability distribution. Exactly.
That's something I glanced over. It doesn't. You can think about it in two different ways. And actually, I didn't go into this. Again, it's something future work. It can be a deterministic model with uncertain initial conditions,
Okay. That's,
right? Or it can be stochastic
yeah.
dynamics, right? But yeah, I do have to know. I'm talking about probability densities here. So yes, I do have to have a model with some uncertainty, whether the uncertainty comes from the uncertainty in initial conditions, or if it's a stochastic model, it's a different story. But I do deal with densities, yes.
Okay. So but somehow you're finding the alphas, the best combination of alphas for the different distributions of the models. But that doesn't necessarily mean that you get a best spread of the ensemble in the future.
No. Well. No, it's not. I can't guarantee that I get the best spread of the ensemble. No, I can't do this. What I can tell you is that I for example, I can tell you that I get a better. Yeah, when you start talking about the spread of the ensemble, it might become a bit tricky.
That's how I'm talking. Maybe
because the spread, I would really, if I were to talk about the model error or the lack of information in terms of KL divergence, that's different. I'm not sure if, because the you know, the spread is a bit different.
I have to think more about what I want to ask than that.
In the way the variance of the truth is given, it's in one of these moments.
Yeah. No, the main thing is that I'm combining the two things. That was the first part that I was trying to sketch. I do need a time window over which I have a good enough statistics, and I don't need to be able to tune the models and decide what's good, what's bad. And then past this window, I can tell you something about how well it will perform in terms of relative entropy.
So this procedure is run over the resolved variables
Yes.
of the model.
Mhm.
So basically, it gives you get after you run through the pipeline, you get one, let's say, combination of ways that you decide. Okay, this is what I'm going to use.
Mhm.
But it could be the case, I imagine, that different models do certain observables better than others. Let's say precipitation versus circulation. So would it make sense to apply the procedure not on the U's, like on the state variables of the model, but rather on observables that you care about, and then you
could
probably different answers.
Yeah, you could. Of course.
So
But what I'm saying, so think about it as a sort of, general framework. I didn't say what the U's were.
So you might not even need to do the least bias.
I know, of course. I mean, this was kind of a necessary step. I mean, I might not have to do the least bias thing if I know. Yeah, but so where was I? This I consider to be the necessary sort of. I'm trying to be realistic here. I'd be happier if I knew this exactly, and if I know the truth without. Yeah, I mean, yeah, but this relationship in a way allows you going past this problem to a certain extent.
Is it correct that the least bias thing is useful if you can compute it explicitly, because then the second term is tractable?
Yeah, I have to know what the least bias densities are. Yes.
So how computable are least bias estimates?
Again, up to Gaussian ones, you probably have to. I mean, based on what I know from people like running big models, I mean, they would say that you can compute Gaussian statistics relatively well even for big models. I don't know what Dimitri would
Subject
say.
to linear constraints or things that you might get from
These are subjects to. I mean, you have to have estimates on the mean. I mean, because my state variable here, for example, would be if I have a discretized model or if I'm running in some sort of spectral expansion, whatever, EOFs or whatever, you could look at the mean and variance of those. You have to have some estimates on the statistics of the variables you're looking at in the training phase, yes. So that's...
And now if you have data, you might have some further linear constraints on that. Is it then still computable?
What constraints are you talking about now?
I think you might know the mean and the variance, and you might observe some linear functionals of the solution.
Yeah, no, you could put them into determining the least bias density. Yes.
As far as I understand, the observations, that's the only thing you have about the truth.
Well, you might have climatology or something. that gives
Yes.
That's observations, yeah.
But that's observations. So this is not the. I mean, I might not be able to compute reliably higher order statistics. So if I because I could just run everything or just on, I could not talk about this expansion here. I could just run everything on. If I assume that I know pi perfectly, I mean, if I know pi perfectly within this window, then I wouldn't need this step.
The L moments are local
The
time.
problem is not so much that you, well, we all know that you don't know pi perfectly. How much imperfection can you tolerate? Because out there in the world, if we're looking at climate models, you know very, very, very little.
About
Much of anything.
well, if I don't know anything, I can't say anything.
But for instance, you want the least biased model. Bias is usually the real kicker in these models.
We're not talking about the same biases. I think what I mean by the least bias, it's just a phrase. Really, it's a term for a particular class of probability densities that gives you that maximized Shannon's entropy given L moment constraint. It's not really to do with the biases that, well, might be related, but doesn't have.
By Shannon's entropy, you have to be able to calculate the probability of something, right?
Yes. No. When I do this procedure, I mean, if I'm looking for least bias for densities which maximize Shannon's entropy subject to L constraints, this is a variational problem. I know what functional form these densities have. I know what the form is. I know it's an exponential family of densities.
I see.
And I know how the constraints enter the problem, and I know it's a convex optimization problem. So there is quite a bit to it. I mean, when it comes to computational, there is. If it's a really big problem, if my state space is massive, then I will just run into computational problems, as probably in many other cases. However, what I could do, and I'm not going to go, what helps you with this problem is one final thing. It's actually, I don't want to, is this statement here. So the relative entropy, if you look at those, it's actually invariant with respect to nonlinear changes of variables, or whatever. It's invariant with respect to the dominating measure, if anyone likes the term, which means that I can introduce changes of variables into the problem without changing the entropy. In particular, I could, for example, diagonalize the covariance, and I could truncate it at some point. I mean, what I'm trying to say is that I think this is a structure for doing further approximations, but it gives you a systematic way for doing further approximations without sort of jumping all over, without knowing what you're doing. That's this is not a silver bullet, and the large state space will be a problem. I'm not claiming to be able to.
I'm just thinking about where one would even start with a detailed Earth system model, even.
Oh, okay. It has started. It's stalled for a while, but it has. There's people at PNNL that I started looking at it with, Pacific Northwestern National Lab.
I know this.
So they were running this on GCMs. They're trying to run it, and it's stalled. But I hopefully it will. But they did.
But how do you start? Because you don't know these things.
I don't know which things.
You don't know PDFs of these big models.
But you can compute them at equilibrium.
You can't compute them. You can sample them.
Well, sorry, I mean sample, not compute them. You can sample. That's what I meant. I mean you can sample them, and they seem to be able to sample them quite well.
Well, you have typically 10 samples. I mean, that's reality.
That's not all I saw, but maybe we're talking about different things. I mean, that's not that.
I think about you showed stuff for climate models. Then we talk about 10.
But I'm not sure if we're talking about the same things. I'm talking about, for example, if you allow your system, let's say, if you allow your system to relax onto its own attractor, and you're looking at the statistics of whatever modes you're decomposing your dynamics in. If you simulate it for long enough, you're going to have much more than that. You can look at the statistics
Yeah, sure.
of whether it's pointwise or whether it's in Fourier space or some other expansion. You can get the statistics of your mode. It's not just 10 sample points. That's what I'm talking about. So you can get estimates on those densities. I don't do this, but what I saw, it didn't look like it was 10, and I know they can do it from way more.
Okay, I suggest we wrap up now. It's nice. All the talks have been excellent. In fact, Michael's in particular was a high note to finish on. So thanks very much.
Thanks.